Hello. This is the fourth video in a multi-video tutorial series using the FluCoMa toolkit to build a two-dimensional sound browser where we can browse and perform sound slices in a two-dimensional space. In this video, the plan is to modify the code so we can load in more sound slices, more sound files, and have more diversity of sounds in our two-dimensional space to explore. Then also I'm going to clean up the code a little bit, so rather than executing all of these operations step by step, it can sort of be executed as one big function that you can load up and perform very quickly. So here is the place where we're loading in the drum loop that we've been using, which sounds like this. And essentially what I want to do here is, rather than loading just this one buffer, just this one sound file into the buffer, and then using that buffer for the rest of my processes here, the slicing, the analysis, etc., I just want to make source, this buffer, have more sound files in it. In FluCoMa, there's an object called FluidLoadFolder, which will do just that for me. It'll actually find all of the sound files in a folder and then load them all into one buffer for me. So the folder that we're going to load here is going to be the folder that comes with the FluCoMa toolkit and has all of these example sound files in it. And we can access that really easily by saying fluid files path. And this will actually just return for me the path to where all of those example audio files are. So if I make this object, I'll call it loader, and then say loader.play. Tell it which server I want it to load things onto, and then I'm going to give it an action function, which I will just have it report back to me done. So now if I initiate this object and then run the play method, it tells me that it is done. So then if I ask loader about its buffer, I can see that here is a buffer that has many samples. It has 2 channels, and it will actually always have however many channels are the maximum number of channels that exist in the files in the folder. So there's a lot of mono files in that folder. There's also some stereo files in that folder. And since 2 is the highest number of channels that any of those files have, this buffer will have 2 channels. And if we want to take a look at what's in that buffer, we can use the fluid waveform object. And we can see that it's 2 channels here. We have L and R. And all of the sound files that are mono are loaded into just the left channel. And any sound files that are stereo have both channels loaded in here in L and R. What I'm going to do for this is I'm actually just going to turn this into a mono sound file using fluid buff compose. First I'll say source equals buffer. So this will be, again, the buffer that we will end up using as our source for the slicing, for the analysis, etc. So I'll make a fluid buff compose here. The server where these buffers are living is on the server S, and then my source here is going to be the loader buffer, which I'm going to copy out of into my buffer called source. This start frame num frames I can leave just as is because these are the defaults, is to copy the entire buffer. However, for start chan and num chans, I'm going to put start chan 0, which of course is the default, but in a moment we'll do another buff copy, another buff compose operation and make start chan 1. And then I'll say num chans should be 1. And then my destination will be this buffer called source. And the dest start chan will be 0. And then I'm going to do one more argument in here, which is going to be gain. And I'm going to make this channel, when I copy it into the buffer source, I'm going to make it at -6 decibels. And this is so that when I copy the next channel into my buffer called source, they'll both be 6 decibels lower, and hopefully then we won't get any clipping. That if we summed together these 2 channels and they have similar signals or the same signal in L and R, we might end up with a signal that is clipping. And then we'll say here, we'll do this buff compose again. But now we're going to start at channel 1. So now we will be copying the right channel, or channel index 1, out of the loader buffer and into the destination source, still at dest start chan 0, because we want to copy both the loader buffer channel 0 and loader buffer channel 1 into destination channel 0. And then there's one more thing I'm going to add here, which is going to be dest gain should be 1, so that when it copies this channel into source, it will not overwrite the information that is already in source that we just copied in right here. It will keep the gain of the audio that's already in source at a loudness of 1 or full amplitude. So now if I run these and look at the source buffer, we can see that I have very similar to what I had before, which we can actually also look at like this. But now just the one channel. And again, what we did here was we copied both of these channels one by one, first the left channel here and then the right channel there, into the buffer called source, which we're looking at here. And when we copied each of those, we copied them both into channel index 0, so that we basically summed it to mono, summed the two channels together, so we have them in mono here in this one buffer. Okay, so now I have a buffer called source that I can use with the rest of this code, because I already have all of this code looking to a buffer called source to be the buffer that contains the audio that I want to slice and analyze and plot. So now let's run some of this and see what happens. So I'll say, we'll use the buff onset slice right here. We'll wait until it says done. And then we'll look and see it has 1,486 slices, which is fine. That sounds great. We can totally use that. I'm curious, one thing I often do here is I want to see what the average length per slice is. That'll give me a sense of how small or big these slices are, and I kind of a sense of like what's in the buffer and how big or small I think they probably should be. So the way I can do that is I can say, I want to find seconds per slice. So I'm going to do the source buffer dot duration divided by the indices dot numFrames. Now, computing it this way is a little bit inaccurate because we actually will have one fewer slices than we have slice points in our indices buffer here, and also because the way that buff onset slice returns the indices of the slice points that it finds in this buffer, it doesn't actually account for the time that we would have before the first slice point that it discovers or after the last slice point that it discovers. However, when we have upwards of 1,500 slices, doing a calculation like this will tell us roughly the ballpark of the average seconds per slice, which is what I'm interested in knowing. So now if we run this bit of code, wait again for it to say done, we can see that the average seconds per slice is about 340 milliseconds. So that seems pretty good to me. So we can proceed with the analysis. So then if I run this, we will get this error, which is because right now it's happening. Here, I'll reboot the server here. What is happening is that we're sending all of this to the server, and it's all getting stacked up on the OSC queue. And remember, all of these operations are being sent in order for each slice that gets passed into this loop as a start and end position. So it was 1,400 and something different slices, and then 7 operations per slice. So you get up into the many thousands of operations that we're trying to stack up in that OSC queue all at once. And so what we're going to do to manage that is we're going to put a sync in here, essentially to sync with the language every so often to make sure that the OSC queue doesn't get overloaded with operations. So if we reboot the server, load our sound, convert to mono, do the slicing, I will reinitialize this place slice function, and then do the analysis. And actually, I'm also going to put in here a little print. So we'll say slice this out of this, and then run this. We can see that we're not getting that error anymore because now the language is syncing with the server for every single slice. So after this processing is done with every slice, the OSC queue is empty. And then we get a message that gets sent back to the language saying, okay, the OSC queue is empty. And then we can send the next batch of operations for the slice. Now, this is great. It's working well. However, we're waiting a long time because we're syncing between every single slice, which is maybe unnecessary to do that much syncing with the server. So what we'll do instead is we will sync every 100 slices or so. So we'll say if I modulus 100 equals 99, because of course I modulus 100 will go from 0 up to 99. And so we're just saying if it's at the end of that modulus cycle, then we'll do this operation, which is to sync. And so now we can see if I run this, that it's happening quite a bit faster because we're not doing all of that syncing, all of that communication back and forth with the language in the server, and now it's done in, you know, a fraction of the time. And we could change this, maybe rather than syncing every 100, we could sync every 200, depending on how many operations we have per slice here. But every 100 for me feels like a fine solution. So, okay, so now we have our data set here that we filled up using add point. And then after we get done with looping through all of the slices, we're syncing once to make sure that we're done with all of this, and then we're getting this print here, which is showing us our data set that has identifiers ranging from 0 to 1484, and then in the column index 0 here has a bunch of spectral centroid values, and in column index 1 has a bunch of loudness values. So now that we have this data set here, we can just take this data set just like we did before and pass it to the rest of this code here. So first I will normalize it just like we did. Here's my data set called normed. We can maybe print it and see. That looks like a bunch of normalized data. And then we will create a KD tree and fit the KD tree to the normalized data set, and then use that normalized data set to plot. And now we have all of these about 1,500 sound slices in this 2D space, organized by loudness from quiet at the bottom to loud at the top, and organized by spectral centroid from low spectral centroid on the left to high spectral centroid on the right. So let's just see what that sounds like. Now, one thing you'll notice is that some of these sound slices are very long. And so sometimes in this case, what I do, because I just want to browse the space and sort of get a sense of what is there, when I play the slice, I don't want to play it for the full duration of the sound slice, because that could be many seconds. So what I do instead is I'll say, let's say var onv here. We'll move this like that. And then I'll say that the dir seconds should be whatever is smaller, the calculated duration of seconds, or just one second. So if the slice ends up being 10 seconds long, I'm just going to play it for the first second and then kill the synth, close the envelope and kill the synth. And if the slice ends up being only 30 milliseconds, then that will obviously be the shorter length here. So then I will just play it for those 30 milliseconds. Okay, so I'll redefine this function. Oh, dir second not defined. Right there. Okay, there's that. And then we'll replot it. And now here's a bunch of high spectral centroid sounds. Gradually get lower. And then over here we have some bass tones. Up here we have loud stuff, snares, and a whole band. And then down here we have quiet stuff. Okay. So now we have this two-dimensional space that we could play around with using not just the drum loops, but some whole folder of sounds that we're using as our corpus now that we might want to load up and play during performance. The next thing I want to do is I want to clean up this code so that we can essentially run it as one function, have this instrument boot up, and then be able to play it quite quickly. So I'll close this, and we'll go up here. And we're going to sort of package all of this into one function. Basically, what I want to pass into the function is my folder. So what is the folder of sounds that I want to appear in this corpus? So I'm going to make an argument here called folder. I'm going to make a new function called 2D instrument. And we'll pass in that folder path and then immediately pass that folder to this object FluidLoadFolder. I'll start turning these global variables into local variables. So I'll say var loader equals, and I can actually just call play on it right there. We're not going to look at it we are going to have a source, and then we are going to do this buff compose operation. So this buff compose operation, we really only need to do it if the buffer of loader has multiple channels. So we're going to check that. In order to make sure that loader is done with its operation, we're actually going to pack all of this in a fork so that we know that we can sync with the server at various times to make sure that these process blocking operations are complete. So right here, I'll say s.sync to make sure that the loader is done with its task. And then I'll say if loader.buffer.numChannels is greater than 1, then we will perform this operation. And if it's not greater than 1, what we're actually going to do is we'll say source equals loader.buffer, because we know that loader.buffer is a mono buffer if the number of channels is not greater than 1. So we'll just set that buffer equal to source so that for the rest of this code, that source variable will be used as our source buffer. I'll put a variable called source up here, but then if we need to actually make source a new buffer, then down here I will say source equals a new buffer that then we will use here to copy into. So let me delete these tildes. We won't display it. We won't play it. We won't use fluid onset slice here, but we will use fluid buff onset slice to do our slicing. I'm going to take this indices variable, move it up here. We won't look at it. We won't do this. We won't display this. But here we will keep this function placeSlice, which I'll just make a variable for up here. Better get rid of all these tildes as well. So we're defining that function still. Here we're not going to loop through all these slice points and play them. We are going to leave our analysis section in here. So I'll get rid of these tildes. Analyses is going to be a data set. I need to make a variable called that here. Because this load to float array has an action function, there's a couple things we might have to do here. We could put a condition in here or something that'll check to see when this function is done, and then when it is complete, move on with the rest of this function. Or we could just start putting the rest of this inside of this action function, which I think is the simpler thing to do here, so we'll just do that. Copy this bit and paste it right in here. Let me get rid of these parentheses. And let me check all this because we have a lot of open and close brackets here. This is the defer, that's good. This is the dump. This guy can go away. This is this fork inside of here, so that should stay. Then we'll have one for the action function and one for the load to float array. Then we'll have to close this fork and eventually close the function. Okay. And I'll put some parentheses on the outside of this function so that we can define it in one go. Okay. So now let's go and check and see. We got to get rid of all these tildes. Better make a variable called normed and a variable called tree. Okay. Now let's see if this works. I think that we this might run for us. Let's just see what happens. So if I define this whole function, it says great, a function. So it has loaded well. And then we'll have to run it and see what happens. So we'll say 2D instrument. And we'll pass a folder in here. We'll just use, again, that folder that comes with the FluCoMa toolkit that has all those example sound files in it. So we'll say fluid files path like this. Then we'll run it and see what we get. It's done the slicing. It's doing the analysis, doing the plotting. And now we have our instrument here. So with this function now, one could pass in a folder of a corpus of sounds and get that 2D performance space very quickly. And also, you know, if you during performance wanted to load up a different folder of sounds, like this folder here, for example, We could just pass in a new path to a different folder, and it'll do all of the same operations and give us another performance space using a completely different set of sounds. There's one thing to notice here, which is that there's one more parameter that we might want to pass into our function to the instrument. And that is that depending on the sound, we might actually end up wanting to use a different threshold for our fluid buff onset slice. So this could be an argument that we pass in. Maybe we want to put it slice thresh here, make it an argument up here. Maybe we'll set the default to 0.05, which is what I just had it at. So that could be one thing to change depending on the sounds that you're using. I will link to this completed set of code in the video description. And in the next video, what we're going to do is we're actually going to not start from this completed function, but actually back up just a little bit and then use a different analysis rather than the spectral shape and loudness. We'll use an MFCC analysis to describe each sound slice with 13 different values, so 13-dimensional space. And then we'll use a dimensionality reduction algorithm called UMAP to organize those 13 values of 13 dimensions in 2 dimensions. So we can have a similar 2-dimensional sound browser, but with a different type of analysis and an analysis that has a lot more features to it.